onto you to see what can be done. I mean,
Yeah.
usually this static and dynamic thing. I mean, you can just play with the weights and change
Yeah.
their
Yes.
moment.
Yes.
So every time we calibrate it and just recalculate the moment.
Yeah.
But
Okay.
I figured out that even if you do the complete balancing, it's still unbalanced. And I
Mm.
figured out that's probably because of the bearings.
Yeah. The bearings could be worn. It could be slightly not, not vertical, or
Exactly.
yeah. Yeah. I think so.
Right, Dima and Dave, thank you very much for joining us. We are now live on YouTube. Thank you for everybody who's joining us on YouTube, whether you're watching this on demand or watching it live in the moment. My name is Dion Knowles. I'm the marketing manager at Tech Equipment, and today I'm joined by two people online. We've got Digital Dave, who's in the Tech Equipment t-shirt here, and we've also got Dima Nasr from Lebanon, the University of Balmain. Hey, Dima, how are you
Hello.
today?
Hello, I'm good. And you?
Fantastic, great, great. So everybody watching us now, what we're going to be doing is Dima's going to be talking to us about women in engineering. Dima studied as a mechanical aerospace engineer. Have I got that right,
Yeah,
Dima?
exactly.
In
Exactly.
Lebanon. She's, we'll tell you a bit more about her career shortly. I don't want to steal Dima's thunder. And in between that, we'll be skipping back and forward to Digital Dave, who will be asking questions. Well, he won't be asking questions. He'll be
Well, I
answering.
might.
Well, you might be asking questions, yes,
Yeah.
but he'll be answering your questions. Questions that you may have about practical teaching equipment, may have about theory relating to engineering. If Dave can't answer it, Dima might be able to help you.
Maybe.
He's also a lecturer.
He's the expert.
Double
So,
trouble.
excellent. See, this is going to be a good one today. Right, so I think we could probably jump straight into it at this point. First of all, I'm going to talk to Dima, if that's okay. Dima, perhaps you could tell us a bit more about your career in engineering as it stands today. I'll hand over to you as you just give us a brief introduction, if that's okay.
Yeah, sure. Well, it all started with me studying mechanical engineering and getting the specialty of aeronautical engineering from the University of Balmain. Actually, it was and it is still the only university in Lebanon that has an aeronautical engineering program. Upon completing that degree, it was a hassle for me to find a job in the aviation industry and the aeronautical field because as most people know that Lebanon is a very tiny country, and the industry in aviation, or the aviation industry in this country, is very small. So there's not much of chance for everyone to get a job here in aviation. So that's why most of the students had to go fetch for jobs somewhere else. For
Right.
us, since we are close to the GCC countries, this is the most suitable place for us to go and look for jobs. So but it was quite challenging for myself because I was a female, and the conditions there are a bit harsh because you have to work outdoors, especially in the aviation industry, and the maintenance of airplanes and so on. And outside is like 50 degrees sometimes during the day. So usually they don't really prefer to have female engineers to work there. But if you look at it nowadays, they have fighting pilots, so fighter jet pilots. So now they have evolved a lot. I mean, things have changed a lot. So back at the time, I wasn't that lucky. But let's say I looked for a job somewhere else, and instead I went for the oil and gas industry, and I worked for an oil and gas contractor. So, but the good thing is that I got a choice. My department had gave me the choice to decide where I want to be or in which department. So I chose the rotating equipment department, where I had to work on pumps, on compressors, on gas turbine generators, on different rotating equipments, and that's where I've built up my expertise in those equipments. And I had the chance to look at them from the technical point of view, and then later on from a management point of view, if you want. And I got the chance to visit so many big facilities, I mean, suppliers' facilities, big, well-known facilities. And that's what the fun part was. But another challenge was there is that, you know, when you work for a contractor in the oil and gas industry, I mean, all your projects are usually either in the desert or in very remote areas where the conditions are not that simple. So the other challenge that came in is that as females, we're not really allowed to go there. So we were allowed to have small visits or short visits for like during one day. We don't get to sleep over on site. So that's another challenge. But I managed to get a few site visits and a few suppliers visiting suppliers, watching out manufacturing processes and checking out testings and so on. So that was quite a good, uh, how can we say, a good exposure. And that's how where it got me today. So I decided to pack my bags and come back home a few years back. And I came back to the university where I have studied. And I'm part of the aircraft maintenance engineering department at the University of Lebanon. And I teach part-time in the mechanical engineering department as well, where I teach lab courses. And that's how I met you guys, because of the equipments in the lab. And with the aircraft maintenance engineering, usually I teach all courses related to gas turbine generators, construction maintenance, and so on.
Brilliant. Thank you very much for that, Dima. That's a great introduction to how you got to where you are today. Now, I'm wondering, what point did you initially think, I want to be an engineer, and what really inspired you and made you pursue that career?
Well, usually people have like they come to this world and they figure out they have a passion for something. It wasn't the case for me at the beginning. When I was very young, I didn't know what I wanted. But then when I grew up and I got to the point of high school, I started looking for options, and I figured out that I can be in a scientific place. I'm not an artist. I'm not into arts, so I'd rather be in a scientific place. And I had in parallel a passion for everything that flies. So I was just passionate about looking at airplanes, how they function, how they operate, and those things. So that's how I made up my mind, and I said I'm gonna try and be an aeronautical engineer, and that's how I got myself into this mess. So.
Very good. Thank you, Dima. I'm going to give you a little bit of a break. I want to remind everybody that those people who are watching us live today, please post your comments, your questions in the chat box, and we'll put those to Dima so that she can answer them during the live session. If you're watching this on demand, then of course put your comments in the comment box and we'll feed those questions through to Dima, or some words of encouragement. That's always great. Let's build everybody up. Now, at this point, I want to go over to Dave Giddings.
I'm still here.
Digital Dave. Digital Dave, as ever, is poised and ready to answer all of your technical questions relating to engineering teaching, whether that might be decommissioning of a piece of equipment over the summer period, whether it might be an explanation of theory or how to run a certain experiment. Digital Dave is here to talk us through it. So do put your questions in the chat box. So Dave, the first question for you today is,
what do we have?
How's your DIY?
Wonderful. I built a gate. I've built a gate.
What have you?
It's not any
Is it a big
gate.
gate or a little gate? Are we talking a little passenger gate, you know, walking gate, or a car width gate?
No, it's about a meter wide.
Okay,
but you know, small steps. Small steps.
Okay, yeah. Very good.
I've had chisels, hammers, jigsaws, bandsaws, paint, creosote, screwdrivers, and patience.
Patience.
Yeah.
How's the patience going?
It's gone.
Oh dear. I can't wait to see this gate.
Yeah. It's work in progress. You might see it next Wednesday.
Right, keep my fingers crossed.
Don't hold your breath.
Well, I showed you on Instagram that next week you might get to see our DIY paper. You can't see it properly there. This is a
No,
life-size mini elephant that I'm making with my 8-year-old son.
the background's not helping there.
It doesn't help.
It's probably a good thing.
Yeah, you know, I know my mother's an artist, but I am not. So my drawing skills really aren't what she hoped they would be.
Oh
It's
dear.
definitely know your weakness.
Yeah,
And
absolutely.
anyway, it will look
Yeah.
interesting. It'll I'm hoping it will materialize. Anyway, let's move on. Proper question now, Dave.
Yeah, come on,
Right.
dear.
Pin jointed frameworks I'd like to talk about at the moment, and I'm going to pull that up on the website as well.
Yeah.
Particular person has asked about just looking at the calculations for this pin jointed framework. And I don't know what kind of calculations, or talking through the experiment that you can do for
Well,
us.
I'll do
Let
my
me
level
pull it
best.
up on the screen. So
You pull it up on the screen and I'll start talking, but I'll do my level best. I assume they're talking about how to calculate the equivalent member forces in each of the members. Okay, so what we've got there on the screen is the STR8. There are 3 arrangements, if you like, you can build with those members. You can do the cantilever, you can run with the Warren girder, or you can go for the most busiest one, most complicated, complex, and that's the roof truss. Okay, so the objective of experiments on all 3 configurations is to calculate the equivalent forces in each of those members that you see there. And you can see that each of the members has strain gauges applied. These go back to a strain meter, a digital strain meter. So there is some information that is already provided in the manual and on the back panel. For example, we are told on the back panel that we have a Young's modulus of 210. Okay, we already know what the strain in each of those members is because we've got our strain meters, our strain meter measuring those strains. So the first thing we want to do is to calculate the stress in each of those members. So we go to a formula where we know already that E, which is Young's modulus, equals stress over the displayed strain. Okay, so we want to transpose that formula to give us the stress in each of the members first of all. Just by a simple little bit of mathematical magic, we transpose the formula to give us stress equals Young's modulus times the displayed strain. Okay, and that gives us the strain in each of the members. So if our Young's modulus is 210 and we have a displayed strain, let's say 120, going from memory, that gives us about 25.2 or 25,200. That's the strain. Now we know that we have another equation further down in the manual. So if we know the stress in each of the members, a formula gives us stress equals force over area. If you transpose that, we can determine the force. So we say that force equals the stress multiplied by the area. Okay. Well, we know what the diameter of the bar is. It's a nominal 5.98 to 6 millimeter diameter. So the area is a well-known formula is pi r squared. Okay. So that gives us a force. So we multiply the force times that previously calculated stress, and that gives us a force in each of the members. And that's the same objective for the Warren girder, the roof truss, and the cantilever. So it's the same procedure. Now I'll carry on. We also said that we are told what the nominal Young's modulus is, However, we are able to actually calculate now the Young's modulus. We know that Young's modulus equals stress over strain. So previously I told you that the stress was 25,200 typically. And I told you also that the strain was 120. Well, 25,200 divided by 120 equals 210, Dion, which
Wonderful.
is exactly the same as the displayed value on the back panel and in the manual. So
Boom.
that's
Well done, Dave.
that's quite a long explanation, but that is the objectives of the 3 arrangements that you see on the STR-8A. There are further experiments in the manual where we look at the deflection example using a dial gauge on the top of the structure, but that's an explanation of the sort of calculations that the students will perform on the STR-8 pin jointed frameworks.
Right, while we're on this, Dave, question that came up previously, and we were talking about putting these into storage and what you need to do, particularly with the strain meters. Is it the strain meters we need to?
There is some good practice to be performed on all of our equipment if they're going into long periods of storage or lockdown. On the structures and on the materials testing, I would say that wherever you have a load cell, like on the STR-8A, for example, you can see the load cell on the bottom horizontal section. Make sure all the loads are in their relaxed state. So all the load cells need to be reduced or turned counterclockwise, so they are in a relaxed state. So no load is applied on any of the members, any of the beams, for example, whilst in storage, because they do tend to creep over a period of time. Okay.
Thanks, Dave. Okay, well, Dave, I'm going to let you have a breather. Dima, we're going to skip over to you now. Dima, what do you love most about being an engineer?
Well, actually, engineering does not have any limits or boundaries in terms of creativity and imagination. So there is a say for Einstein. I think that science has some kind of limitation, but there is no limitations and limits to creativity. So creativity is part of engineering. So either if you are a very creative person or no, you can still be an engineer, because either you can come up with designs and invent stuff, or you can fix stuff or find stuff and make them get to work better. So that's the good thing about engineering, is that there is no right and wrong. It's how you see it. If you see it correct, it's correct. If you see it incorrect, then it's incorrect. So and there is no right or wrong design, to be specific. So so that's the good thing, that even if it's pure science, you can still find a very subjective part in it. It's not really objective. You can still look at it the way you want to see it.
Fantastic, thank you. Interesting, good perspective on that there.
It's probably some philosophy that I've came up with myself, but this is how I see engineering.
Brilliant, good. And you explained your fascination with engineering is about flight. Were there specific things when you were younger, when you really, I don't know, you flew in an aeroplane and you thought, oh my gosh, yes. Was there an actual trigger point? Can you remember a trigger point or not?
Well, I was always curious about that noise you hear when you're like flying in an aircraft, because flying is it's something that comes from nature. I mean, birds can fly, and that's how engineers came up with airplanes, by just observing science and nature and airplane and birds, and then just coming up with the fact that wings can get you to fly. How? Using certain theories. But I was just fascinated by the noise that you can hear, and that effect when you're taking off or when you're landing, and or this change in power setting within an engine. So Do I look like I'm talking about a cake or something? I don't know. I really just get so in it. So that's my trigger point actually. That noise and the fact that you can change this noise and then you get to have a higher power or a lower power. I mean that whole magic that was going on within an engine. So that's what is my was and still my ongoing fascination.
And when you were at I guess in secondary school, high school, and you decided I want to be an engineer, what was the response from your peers around you as to that choice at that time?
Well, at first, usually people decide, I mean, make career choices based on their background or some family obligations or some family influence and so on. It was not the case for me because none of my parents were engineers, and nobody in my family was an engineer, especially aeronautical engineer. But once I mentioned that I want to become an aeronautical engineer, I mean, at first they thought I was joking, and they were like, "Sure, go ahead." And then when they saw I was really serious about it, and they were like, "Okay, if this is what you want to do, if this is what you want to spend the rest of your life doing, just go ahead." I mean, and even till now, I still get their support in one of those weak moments. And even during my career, when you have those little frustrations about jobs and so on, I mean, they were always there. Nobody had to stand up and say, "Oh, we told you you're not gonna find a job," or "We told you it's gonna be difficult," and so on. No, at all. They were like, "No, this is what you want to do. You go ahead and do it." And I can say that I'm very lucky to have such support from, especially from the peers and family around me.
Brilliant. And what would you say to young women out there who are thinking about engineering? What would you tell? What would be your big message, I suppose?
Well, I mean, the first and the last thing I would say to people, to young women or even young men, if you want to do it and you have a passion for it, just do it. I mean, just don't don't count on anyone else to motivate you or to push you to do it. If this is what you think you can do or you want to do, then go ahead and just don't think about challenges and obstacles that you might face, because everyone does in their life, regardless if they are engineers or no. And just do it because you love to do it, not because anybody or anyone has said you have to do it. And don't do it because people, especially for women, don't do it because somebody said, "No, you're a female, you cannot do it." Just do it because you know you can do it. I mean, don't waste your energy on proving to people that you can do it. Just do it. It's probably looks like a slogan for Nike. Just do it, but yeah, it is. So,
I was thinking, what trainers are you wearing?
I know I'm not a big fan of Nike, so I'm more into an Adidas person. So
Right.
Very good. Good
I
answer.
just like that. I just do it. So
Fantastic. Good. Thank you, Dima. We'll come back to you shortly. I'm going to skip back over to Dave now. Dave, I'd like to talk about the static and dynamic balancing experiment
Okay.
now. I'm going to
Yep.
pull that up on the screen for everybody to see. This is a really popular
It is
piece
popular.
of equipment
That'll be
because
the TM 1002.
correct, it is. Here we
Yeah.
go. We've got some nice footage of it here. Right, Dave, I think we've had a question. Somebody on YouTube was wondering about why is it that we need to use two masses to achieve dynamic balancing while one mass is sufficient for static balancing? That's not a 3-year warranty, by the way. It shows 3-year warranty on this video. We offer a 5-year warranty. Just correcting that there before you jump in.
Just listening to your paragraph there, that doesn't quite sound correct. Let me just give you a little bit of background on the TM1002, and maybe if that viewer is watching again, it'll make a bit more sense. But the rules of balancing a shaft, okay, if a shaft has masses mounted on it, they can be both statically and dynamically balanced, okay. So if it is statically balanced, Dion, that means the shaft will stay in any angular position without it rotating. Okay. If it's dynamically balanced, it can be rotated at any speed without any vibration. Okay. So if I move on to the first experiment in the Tech Equipment TM1002, we aim to show that a two-mass system can be statically balanced, but it cannot be dynamically balanced. Okay, so here we have on our TM1002, we have a shaft, and the user will mount two weights about 100 millimeters apart and 180 degrees out of sync of each other. Okay, so to do the static test, we rotate the protractor on the end of the shaft and we prove that it is statically balanced because it doesn't rotate in any angular position. Why is that? Well, because the moment, or the turning moment caused by mass 1 is a clockwise moment, but on the other weight, because it's 180 degrees out, the moment caused by the mass is anti-clockwise, and it therefore clockwise is opposing the anti-clockwise. So it can be rotated at any position by hand without any movement. However, if we then turn to the dynamic test, when you press and hold the button briefly on the motor, the user will note a severe imbalance, proving that it is dynamically unbalanced. Okay. Further analysis can show that there's also a twisting motion, showing the dynamic twisting moment. So that paragraph doesn't quite ring true to me. Maybe we got a little bit mixed up with the terminology there, Dion. Okay. So that our experiments the first experiment looks at two masses 180 degrees apart. 180 degrees apart, and we prove that it can be statically balanced but dynamically unbalanced. Okay, with two mass system.
Great. Thank you for that, Dave. Much appreciated.
Okay.
Before we go on to another question for you, Dave, I'm going to hop back to Dima.
Okay.
To talk more again about women in engineering. We constantly hear about increasing the amount of women in STEM and in engineering. Why do you think we continue to have this challenge to get more women involved in these disciplines?
Well, I think because at first when everything started, I mean, this whole STEM business was a kind of entitled to men only, and because engineering work was a bit tough, especially back in the very old days, from railway station engineers and so on, it was quite challenging for women, and the role of a woman was defined to stay within her family and so on. And because every family is, or children and whatsoever, are more dependent on their mother than on their father. So that's why some women feel like they have to make a choice. It's either engineering means long working hours, tough job, site visits, dirty work probably, and others to decide that I got to find a simpler job, stay home, help raise my family, take care of my kids, and so on. So I think it has to do a bit with psychology. I mean, and how women think. That's what I personally think. But the way I see it is that either way, if you are out there working or staying at home, you have to be a good example for your family. And by being a good example, I mean showing your family how you can help society, how build up society, find solutions to the world, help the world to be a better, try to make the world a better place. So this is why we need to change our mind setting into looking at the fact that no, you're not giving up your family. You're just doing something else. You're trying to motivate your family and especially your children to be better people.
Yeah, I think that's a really good point about being a role model and showing say, your kids what is possible, what you can achieve. And sometimes, yes, that does involve going away and doing things like that. And
you to yourself and you see it's not that simple, but you can at least try.
Yeah, you can. And I think they see it as they almost look up to, I know my own experience from my own child, my own daughter, for example, actually. And sometimes she has found it tough when I've traveled for work in the past. But at the same time, she says, well, I'd really like to do a job like you, mummy. And that's kind of heartening in a way, because I don't want her to be me and do the same as me. But at the same time, she has aspirations to want to go out and make a career for herself, I guess.
Exactly.
Good. Thanks, Dima. I'm going to skip back over to Dave again now. Dave,
Hi there.
thank you for coming back to us. My question now is, bending moments, variation away from the point of loading experiment. We did a little YouTube video on this recently. I think it's Tanisha did a little tutorial on it. And they wanted to have a bit more of an explanation of the theory. And you very kindly put together a nice diagram for us to look at.
Yeah, I can talk about the content of that if you like.
Yeah, I'm going to try and share the screen with it at the moment. Problem is I have it on the wrong way around, so everybody's got to tilt their head to the side to make any sense of it. Let me see if I can help.
Oh yeah, I remember
display
doing
it better.
Yeah.
Do you think you might be able to explain more about
this is looking at this is the STR2 bending moment. This is a very straightforward, simple experiment where we look at an experimental bending moment compared to the theoretical bending moment. So we have on that spreadsheet a low row of columns. So we have a mass in grams, that's then converted into newtons of force. That's quite a simple, straightforward conversion. We have an STR1A digital force meter, and that's measuring the load at the cut in the beam. So we have some values there, 0, 0.8, 1.4, 2, etc. Now, by nature of the design of the STR2, the experimental bending moment at the cut actually equals the displayed force on the STR1A multiplied by 0.125 of a meter. And that gives us our experimental bending moment, okay? But the maths involved is when we want to calculate the theoretical bending moment of the cut of the beam. So we have an equation which is WA brackets L minus small a divided by L. Let me just tell you what those mean. That means the W is the load that's being applied on the weight hanger. L is the overall length of the beam between the supports, okay? The A value is the distance from the left-hand support to the cut in the beam, all right? So then we go back to the equation, we put those values in because we know the load applied, because that comes from the force meter. We know the length of the beam, we know the A value. Therefore, we can then plot a graph with two values or two traces. We can plot the experimental bending moment, and we can then plot the theoretical bending moment, and they should be close. They will never be exactly the same, Dion, because of the real life friction and the sticking, etc. But you can see from that graph that they do follow pretty much the same course. Okay,
brilliant.
So that's my answer.
Thank you for that, Dave. We've had a question from Murugan. Murugan's on the line today. And first of all, I'd just like to tell Jeff, I'm ever so sorry, Jeff, I can't get the image to rotate here, which is annoying. I should have had a bit of more advanced foresight before jumping on the meeting. Next time.
Well, we can share that. We can share that with anybody.
Yeah. we'll pop the URL of this into the comments box after the live webinar. Okay, so Murugan's question now is, are there any products which have the facility for remote hardware experiments? This is a question that we are getting asked quite a lot at the moment, as you would expect, as people are in remote offices. We really focus on the practical teaching, don't we, Dave?
We do, yeah. And none of our equipment is computer controlled. It's all relies on the user, the students, to get their hands dirty, roll up their sleeves, and so on. Some of the control engineering, like the T3300s, they are controlled by software, but even though I've never known it to be more than a few meters away, and certainly not remotely like a SCADA system, for example.
There is an option with some of our structure software for understanding structures in more detail, to do simulations standalone without using the apparatus itself.
There is,
but we'd be able to talk to you more on that on an individual basis.
Yeah.
Okay, right. So I'm going to hop back to Dima now. I think we're almost getting towards ready to wrap up shortly for this particular session. Let's go over to Dima for a little bit of a wrap up. Dima, what would you say to young women, anybody, women or girls who are interested in pursuing a career in engineering? What would your big takeaway message be to them?
Well, I mentioned a little bit about it earlier, that it would be that if you want something, you just better work hard for it, because life is not easy, and you have to put up with some sweat, because especially the engineering field, it's not something very simple to anyone, even for men. So but don't waste your energy, especially being a female. Don't waste your energy trying to impress people and say, hey, I am a woman and I can do it. You just go ahead and do whatever task or job you have to do. Because at the end of the day, I mean, if they have a problem with you, or if they have any doubt with your capabilities of doing something or no, then it's their problem. It's not your problem. Your problem is that you have to work hard to get that degree, or to get that career in engineering, or to get that dream job you want, or anything you want in engineering. But you just don't worry about whatever you see on the sides of the road while going there. That's none of your business. Let them worry about it. Just focus on whatever you need to do, and go ahead and do it. And don't worry. Life is full of surprises. Even if you face some challenges, you might get some nice surprises at the end.
Oh, brilliant. Really great message to take away from that. I believe that's probably pretty much it from us today. We haven't had any more questions that have come in. Dima, thank you so much for joining
thanks, Dima, for your time. Always a pleasure.
Thank you for you. It was a pleasure for me as well.
Brilliant. This will be available on demand. Many people may well be watching it on demand now. Feel free to put your comments in the comment box below. Give Dima a big thumbs up. Follow the TechWhip YouTube channel as well if you want to, and we're on Instagram as well. We will be back next week, and the exciting thing about next week is we have yet another guest speaker. Guest speaker for next week is Judy Raper, and she is the dean of a new university that is setting up in London called Teddy London. They're approaching the teaching of engineering in terms of a project-based approach. Very, very different. It's not a lecture-based learning approach. It's about getting hands-on, solving community problems through projects, and learning as the project progresses. So Judy will be online talking about that concept, and answering any of the questions that you may have during that live session. And Digital Dave will be back. Dave, thank you so much again.
That's right. Pleasure, Dion.
Sharing your wisdom today. Yeah, thank you very much, and goodbye.
Bye now.
See you.